Cool. Let's see, the practice exam for the final is posted. As promised, it does cover chapters 10 through 14. So that's a thing to be thinking about. What else? I think that's all I want to say for now. About that, at least. So the plan is to finish chapter 13 today. There are 2 videos for today that I hope you were able to watch. And that finishes out chapter 13. And then Wednesday and Thursday will be chapter 14, which would be sound. And not everything we talk about in chapter 14 will show up on the exam, but I'll let you know what items do and what items don't. Yeah, I'll let you know. So, so let's move forward. If you're wondering again what shows up, what is and isn't on the final exam, looking at what's on the final and what concepts don't show up on the practice exam, what items don't show up on the practice exam, is a pretty good indicator of the things that don't show up. Again, it's just a couple items from chapter 14. So let me share the appropriate screen. So we're looking at vibrations and waves again, or still, I suppose. So let me remind us of what we've done. Really, I think I want to look at these graphs. So, man, there's a lot of ink on this. Let's make some of this go away. Doesn't matter much anymore anyway. All right, so we have position versus time. This is for simple harmonic motion of like a mass on a spring, right? So position versus time is like a cosine. Velocity versus time is out of phase with that, right? So it's a sine. And acceleration versus time is out of phase 1 more quarter step. So it's a half cycle out of phase with position, meaning when position is a maximum, acceleration is a minimum, and velocity is 0, right? And then when position is 0, velocity is at a minimum or maximum, and acceleration is also at 0, but it's going the other way. These 3 equations, right? They're almost all in orange. Let me make the last one in orange. See if I get the right orange. More or less. There's position, velocity, and acceleration as a function of time, right? They all are related to this omega, which is related to period and frequency in this way. Again, omega is just angular frequency. It's very analogous to angular speed when we talked about circular motion. And all of these equations are summarized on the front page of this handout, I think. We're almost there. Yeah, I think they show up on the equation sheet for this as well. So you can take a look at that. Let's do an example. I want to do example number 3, I think. Yeah, example number 3. Someone have a question?
Yeah. It's more of kind of a conceptual question. Is A and X, like, are they equal to each other?
No, A is acceleration and X is...
Or not for that, sorry. For
Oh, I know what you're saying. You're saying amplitude.
Yeah.
Yep, I'm with you. Yeah, so I have said X of t is A cosine omega t. A is a more generic term for like how big the oscillation is. So we've used amplitude for, say, like how far a pendulum swings, right? Because a pendulum is simple harmonic motion as well. So X max, the short answer to your question is yeah. When I say X max, I do mean amplitude. That's the amplitude of the motion. But I suppose you could say the amplitude of the velocity here is V max, and the amplitude of the acceleration is A max. Right? So amplitude is a general term for how big the oscillation is. And if I'm talking about a specific motion, I might want to label it more specifically. Does that make sense?
Yes, thank you.
Cool, awesome. Thank you for asking that question. It's a great question. So yeah, let's do some examples. I want to get to example 5, but let's just start pushing through these, and I think we'll just get as far as we can. So example 3 has a graph of position versus time for something in simple harmonic motion. Doesn't even tell us what it is, right? But it doesn't matter. It doesn't matter what it is, because there are bits of information that anything that's in simple harmonic motion will follow, right? So I have this, it looks like it's a sine or a cosine. It's not technically either one because it's not starting at 0 or the maximum. But what are we looking for? Amplitude and frequency. So amplitude and frequency. Amplitude is how far from 0 this thing goes. So let's label that as this green. So that's my amplitude. Or I could go down this way and call that my amplitude, right? What I want to be careful of is it's not from top to bottom, it's from top to middle or bottom to middle, right? So we'll make that go back away. So my amplitude is 20 centimeters. Right? Read directly off the graph. And what's the frequency of the oscillation? Frequency I can't get directly off this graph, but I can get period, right? Remember, period is, yeah, that's fine. Period is a peak to peak distance, so I could do like this bit, or I could do this peak to this peak. So how far is that? Both of those are a period. That's harder to tell. It looks like it's the same distance as 2 to 6. So I'm going to eyeball that and call it 4 seconds. You guys buy that? Right?
Becker?
This, yeah.
Could you just say that there are, it looks like two full periods in 8 seconds? Because it starts at -10 and stops at -10? Or can you not infer that from the graph?
No, I think you could. I think you could. And if you did
Okay.
that, you would get 4 seconds. So that's spectacular. Yeah. I was going to do something tricky. And nope, not that. Oh, come on. I want to take advantage of the format and slide one of these to see like, oh, it really is 2 to 4. I don't think I'll ever be able to teach with just like a regular ink pen again. We'll see what next semester looks like. Okay, so my period is 4 seconds. What does that mean my frequency is? Well, frequency is 1 over period. So that's 1 over 4 seconds, or 0.25. That doesn't look like a 2. See? And my handwriting is not any better when I'm using an ink pen. I do slow down a little bit because there's 0 resistance when you're writing with this thing. So 0.25 inverse seconds, which is 0.25 hertz, right? Okay, questions about this problem? Fantastic. Moving forward, I like this example. As example number 4, some passengers on an ocean cruise may suffer from motion sickness as the ship rocks back and forth on the waves. At one position on the ship, passengers experience a vertical motion of amplitude 1.4 meters and period of 17 seconds. What is the maximum acceleration of the passengers during this trip? Oh, yeah, so this would be a great way to quantify the likelihood of someone getting motion sickness, right? We're looking at maximum acceleration, right? So what is Amax? Well, it's related, we can go back up here. It's related to, there's so much junk on this. Omega and Xmax, right? So Amax is omega squared Xmax, and there's a minus sign, but really all I care about is the magnitude, right? That minus sign just tells me that A of t is upside down compared to x of t. Okay, so I'm not given omega, I'm given a period, I think. But omega is related to period. I'm being sloppy again, this way, right? So this is all the information that I need. So we'll look at it hard and we'll remember it. Go back to that page and write it down. What page we're on? Ah, this one. So x max is omega squared, sorry, a max is omega squared x max. And what else? Omega is related to period as a 2 pi over period for omega. So I can put those together with the information that I'm given here, that x max is 1.4 meters and the period is 17 seconds. So if I put all of that together, let's do omega first. So omega is 2 pi over the period is 17 seconds. So what I get for that is whatever 2 pi divided by 17 is. Do I have that solved over here? Scroll. I did. Fabulous. 0.3696 radians per second. How do I know it's radians per second? Well, the fact that a 2 pi is in there is a pretty dead giveaway that it's radians. But I also know omega has to have units of radians per second. So if the equation was derived correctly, that's the unit it's going to come out in, because that's the way SI units work. So there's omega. And now I can solve for A max, which is omega squared times x max. So that's 0.3696 radians per second squared times 1.4 meters. And if you do that, you get 0.19 meters per second squared. Okay, is that big? Is that small? Well, at one position, passengers experience this. I guess they don't tell us whether passengers are getting sick there. It probably depends on the passenger, right? But I can tell you the fraction of g that is, right? So what fraction of g is it? Well, it's A max over g, right? So that's 0.19 meters per second squared divided by 9.8 meters per second squared. So that's basically 0.2 divided by 10. So that should be 0.02. So that's like 2% of the acceleration due to gravity. Although we don't normally experience the acceleration due to gravity, right? Because we're not actually in free fall. So questions about this problem? Mostly we're just stretching our math legs here, kind of exploring the equations. Speaking of exploring the equations, what if I was just given the equation of motion of a simple harmonic oscillator? Could I grab all of the information out of it? So this is this is example number 5, right? This is the equation of motion of a mass on a spring. So let's see if we can get all of this information out of there. So how would I get the amplitude and the period and a spring constant out of the equation and a mass? Well, let's at first just label these things. So the mass given to me, it's 0.046 kilograms, right? You've got to move that 3 places. And the equation, to get information out of that, here's what I like to do. I would like to write the equation in variables right above the equation with numbers in it, right? So the equation in variables, again, I can grab this out of from the first page of the lecture handout. It's also on the equation sheet. Some amplitude, which is x max, times cosine omega t, right? So then just comparing them directly, I can see, oh, amplitude must be 1.9 centimeters and omega must be 10 radians per second. So that first bit tells me this first answer. 1.9 centimeters. That's not the SI unit, but it is correct. So we'll just call that good. Determine the period. I don't know period directly, right? But I do know omega, and I know that omega is related to period this way, right? So that means period equals 2 pi divided by omega. So I can just plug that in. 2 pi divided by 10 radians per second is going to give me 2 pi. No, math doesn't work that way. I would actually multiply it out, right? I know often in math courses you leave answers in terms of pi. There are only some cases where I would suggest doing that. In physics, by and large, we just multiply it out, right? So 2 pi is like 6.28 divided by 10 is going to be 0.6. Is that right? Yeah, 0.63, we'll round it. And that's in seconds. Questions so far? Cool. So determine the spring constant. So for a mass on a spring, there is a natural frequency, right? It's if you just set the thing oscillating, it oscillates at a frequency that depends on both the calendar. What's happening at 6:30? My apologies. It depends on both the mass and the spring constant. As a reminder, that is, I see, I understand what's going on. That is, we can do this. Period is 2 pi times the square root of m over k. I also know that omega squared equals k over m. I can also relate this to frequency. Frequency is 1 over 2 pi times the square root of k over m. Right, so these are all equivalent because omega is related to frequency as well. Does that make sense? So I can take my pick, right? I can use any of these equations. Maybe I'll use the omega squared equation because that looks like I don't have to worry about any square root signs. So k looks like it's m omega squared. So I can plug that in. The mass is 0.046 kilograms, and omega is no, it's not, it's 10. Oh, that's fabulous. I can square 10. I can do that in my head. 10 radians per second. Squared, right? So if I square yeah, great. If I square 10, I get 100, and I multiply 0.046 by 100, I get 4.6 kilograms per second squared. Kilogram doesn't look okay. Okay, but that doesn't feel like a unit that I'm used to, kilograms per second squared. The unit that we're used to is newtons per meter, but a newton is a kilogram meter per second squared. So if you divide a kilogram meter per second squared by a meter, you get kilogram per second squared. So either one of these is correct, but the newton per meter is a little more like meaningful. All right, okay, so we've got like, let's just do these last two and then move forward. These two, D and E, we'll leave F. Leave F out in the cold. So determine the maximum speed. So Vmax, we have an equation for that. Right, remember, just going to the front of the handout. Vmax here is omega times Xmax. So we can come back and just plug that in. Omega times X max, and X max is the amplitude, right? So I actually have both of those. They're given to me directly in the equation. So omega times the amplitude is 10 times 1.9. So that's going to be 19 centimeters per second. You buy that? 10 radians per second times 19, is that right? What was it? 1.9. So that's 19 centimeters per second, or 0.19 meters per second if we're trying to be in the SI unit. And finally, we get to answer, what is the total energy of this oscillator? So I don't remember if I've talked about that in a live lecture, but I talked about it in the video for sure. The energy of this oscillator is going to be K plus U, right? And what do we have? Well, the oscillator is moving, right? So it has some velocity, but the velocity is changing always, right? It's going faster, then it's going slower. We also have spring potential, right? And the spring is constantly stretching and compressing. And it turns out this total is a constant. All right, and I did the math for that in the video for subharmonic motion. You have to remember that cosine squared plus sine squared equals 1 to prove it. So that constant I can get from adding up the total energy at any time in the motion, but it's useful to add at specific times. Specifically, when all of the energy, when all of the energy is kinetic, so we could say K max, or when all of the energy is potential, U max. Right, so to do U max, I need the spring constant and the amplitude, which I have, and to do K max, I need the mass and the velocity maximum, which I have. So let's do it both ways. That'll be fun. Said without any sarcasm whatsoever. Seriously, I'm actually excited about it. Okay, so K max is half mv max squared. Does that make sense? Just half mv squared, and it's the biggest velocity, so you plug it in. So we could do that. Half times 0.046 kilograms times that velocity we got. And we should probably plug that in SI units if we want joules to pop out of this. So that's 0.19 squared. Okay. I could do a little better. So if you do that, 1/2 times 0.046 times 0.19 squared, I get 8.3 times 10 to the minus 4 joules. But I said you could also do U max. And the spring potential is half K x squared, or delta x squared. But for maximum, I need x max. So often we just put the amplitude there. So I could just call it a squared or x max squared. So I know all of these things. That's half. K is 4.6 newtons per meter, and the amplitude was 1.9 centimeters, and I need that to be in meters, so it's 0.019 meters squared. Is that right? Yeah. You look at that. Half that 4.6 and that 1.9. It's just we've moved the factor of 10. It's a factor of 100 actually, to a different part of the system. If you do this math, you get exactly the same answer, which is not surprising because we proved that mathematically already. And again, at any other point in the motion, the total energy will still be this number, right? It's just easy to calculate for one of these extra. Is there a question about this? How's this feel to you guys?
I had a question about part D.
Okay.
How did you get the equation for Vmax? I was looking at the top of the worksheet and I wasn't sure how you derived that.
So how did I derive it? Calculus.
Well, maybe that wasn't the right word then. I don't know.
No. It's not wrong. It's just, I just want to answer your question the way you asked it. So here, Vmax here is the same as that bit. Or you can do this line. That's a little too bold. Guess that's why highlighters are yellow. That's fine. Does that answer your question?
Well, so would it be negative then?
No, we're just looking for a maximum speed. The direction is not super meaningful in the context of this problem.
Okay.
If we said we've got a mass on a spring and it's yeah, the short answer is the context of the problem dictates whether the sign is meaningful or not. In this case, it isn't.
Okay.
That's a reasonable question, though. Other questions? Okay. So the next thing I want to talk about is traveling waves. So I introduced this in the video, the first video for today. So 10 of you are familiar with it already. Instead of that, let's talk about pendulums, because I haven't talked about that anywhere yet. We should talk about that. I would love to go through the derivation of this, but I don't have the time for it. So you did a lab today or yesterday about pendula, right? So what is a pendulum? It's a mass. This is a simple pendulum. The other thing you can talk about is what they call a physical pendulum. This would be like if you have something that is not a point mass and you let it oscillate. Don't hold it that way. Oscillate. Then you have to worry about the moment of inertia of this thing and the center of mass of it. But for a simple pendulum, we're just thinking there's a length, there's a mass, and you can pull this up, and it has some kind of amplitude, right? So this would be like theta max. So what you can do with this is you can say, well, what kind of torque is created? What kind of torque is created by the gravitational force on this? Well, it depends on theta. So there's some torque, which is basically our restoring force. And you can find that torque is proportional to minus theta times some constant. I think it's G over L times theta. All right, which looks a lot like force equals minus kx. Don't quote me on that. This may not be exactly right. The result, though, is this, that you can find that the period for a pendulum is 2 pi times the square root of G over L or L over G. It's L over G. Let's get it backwards. So what you notice is mass doesn't show up and amplitude doesn't show up. Right? So at least my lab, you looked at how period relates to mass, amplitude, and length. And what you should have found is that mass didn't affect the period, amplitude didn't affect the period, at least not much. And length did. And if you took more than 2 or 3 data points, you may have seen that it wasn't exactly linear. 3 is fine though, because you wouldn't necessarily have known to plot period squared versus length. The thing you couldn't control, which you maybe wouldn't have thought to control, is the acceleration due to gravity. So if you take the same pendulum to, say, the moon, where g is smaller, that pendulum will tick more slowly, right? So like a grandfather clock that's designed to work on Earth won't work correctly on the moon, right? It'll tick time too slowly. You could fix it by changing the length, though. The gravity on the moon is 6 times smaller than that here, so you'd have to reduce the length of the pendulum by a factor of 6. Hey, that's exactly what this question is asking. I hadn't read the question yet. Let's do the question. I hope that's what it says. Oh yeah, that's exactly it. Right? So we could solve this stepwise, but the argument that I just made is what's going to work. So I'm going to erase some of this stuff just so I have some space. Come on. I'll move that over here. Okay. So free fall acceleration on the moon. So I can say G moon is 1.62 meters per second squared. So what is the length of a pendulum whose period on the moon matches the period of a 1.8 meter long period, pendulum on Earth? So G moon is this. I wanted a length moon if G Earth is, 9.8 meters per second squared, and length Earth is 1.8 meters. So we want the periods to equal, right? That's what they're saying. Whose period on the moon matches? Yeah. So, so I could basically say this. Period equals 2 pi times the square root of L over G. That should be L, let's say L Earth divided by G Earth. But I also want it to equal 2 pi times the square root of L Moon divided by G Moon. Do you guys buy that? Because I want T Earth to equal T Moon. So I can do some math to this. By the way, in the handout, I did this by solving for the period and then plugging back into the equation with a new G to find a new length. But I like what we're about to do better. Although admittedly, it's a little more, it takes a little more math abstraction, but it's equally correct. So I could divide both sides by 2 pi. And then I could square both sides, which makes the square root go away. So now let me write another line. So what that means is L Earth over G Earth equals L Moon over G Moon. And that's a simple equation, right? And that lets me answer this question very quickly, because again, G on the moon is about 1/6 of G on Earth, which means the length on the moon needs to be 1/6 of the length on Earth. Or basically, you could plug these things in, right? 1.8 meters divided by 9.8 meters per second squared equals length on the moon divided by 1.62 meters per second squared. And what you get for the length on the moon is pretty close to 0.3 of a meter. Questions about that? Cool. So let's talk about traveling waves a little bit. Again, I talked extensively. I think I posted a 27-minute video about it today. So I'm not going to reintroduce it right now because it would take me, 27 minutes. Oh, hey, I lost my screen. Come back. There we go. Suffice it to say, a traveling wave is motion in both. I think the best thing to do is to go to coloring. Just joking. Let's not color. Where is it? I had some animations up. Transverse wave. Here's my transverse wave. Oh, that's beautiful. So the idea for a transverse wave is, so there is a medium, right? So the medium in this case is a spring. This would be like a slinky. And you move one part of the slinky. So each part of the slinky, each atom in the slinky is undergoing simple harmonic motion. But because the atoms are connected together and sitting next to each other, that motion of one atom translates to the next atom, translates to the next atom, and you get motion of energy down the medium. All right. There's another animation that I really like. It's this one. All right, what I really like about this one though is when you can see it for a longitudinal wave. So this is a transverse wave. Like waves on strings are transverse, meaning the atoms move up and down and the wave moves, say, to the right. You can also have a compression wave or a longitudinal wave where the motion of the wave and the motion of the medium are in the same direction. Right? Again, the medium is not moving overall. It's just atoms in the medium are oscillating, but there's energy moving one way or another. Okay, so let's do, I did that example. Where's 8? Almost out of time. Did all the good examples during in the videos. I think I did that one too. I guess since I introduced that, let me introduce standing waves for a second, and that'll be a taste of, if you haven't watched the videos, what you can see in the videos. Otherwise, the rest of these examples are pretty simple. So a standing wave, and again, this will take me not as long as, not very long. Let me go back to this guy. Oh, Chrome didn't shut down correctly. That's fine. Standing wave. Here, a standing wave is if you let a wave oscillate, or sorry, bounce off of one end. So the example I gave in the video is you take a jump rope and you tie off one end, and if you wiggle the jump rope, like send maybe a pulse down, it reflects off of the end and comes back at you. And if you send another pulse toward that pulse coming toward you, they can interfere with each other. All right, and if you oscillate that at the proper frequency, you can get a standing wave. Right? Maybe you've tried this before. If you haven't, I suggest you try it. It works really well with a slinky. Just don't use too high of an amplitude or you'll end up with a slinky nest. But anyway, you can get several different modes of oscillation for this, and that's what we're looking at here in this animation. So I described this mathematically in the video, and I worked a couple examples. So I would suggest, if you haven't seen those, to look at those. Let me ask before we wrap up today. Any questions? Do you guys have any questions? No. Cool. Okay. Yeah, so I haven't worked all of the examples for this, but I think the ones that I haven't ended up in a video are pretty straightforward. So take a look at those, and if you have questions about them, let me know. Otherwise, we're going to move forward to chapter 14 tomorrow and Thursday. So thank you so much for joining me in my basement while I talk about physics for 40 minutes. I'll see you guys next time.
Bye.